Okay, so welcome to CADEPS once again. So today we have Elizabeth Gasparin, who is going to talk about homological mirror symmetry for adjoint orbits. Okay, Elizabeth, please.
Okay, thank you for the invitation. It's been, I think, about 10 years since I was in IMPA last time. That time I was speaking at the symplectic geometry seminar. Okay, so, and right now I am at the University of Trento, and we are in research in pairs, which means 3 people at the moment, this pair of 3. So with Eduardo Balico, that's online also, and Bruno Suzuki, who's here right now, but is actually a postdoc at USP. Okay, so let's see, homological mirror symmetry. I gave this abstract. So I will describe the homological mirror symmetry conjecture as a duality between symplectic and algebraic geometry. And you will see I have football slides, which were made by Bruno that I've been using for a while. Of course, mathematics should not be like football, so it's not one area against the other. But in this particular case of the conjecture, it's actually interesting to present it as a game between symplectic and algebraic geometry. So I'll do it like that. Let's see. All right, so I start with the integration. The slides were made for some people who didn't know Hodge theory, so you don't need that, but here it is. So the beginning is just the claim that the most important thing that we teach in undergraduate mathematics are integrals. So here are the integrals. And this was my motivation for the HPQ cohomology for a group of people who didn't know it. But you guys do, of course. So let's go with the Hodge diamond, because I want to talk about some type of mirror symmetry. So the first thing I need to say is, what's the mirror? So that's my first objective. So if we have the Hodge diamond of a smooth projective variety, then such a diamond has 3 symmetries: Hodge duality, Serre duality, and conjugation, which give symmetries over the horizontal line, the vertical line, and the rotation, so that the entire diamond is determined by this one red corner depicted here by reflections and so on. So these are the classical symmetries of the Hodge diamond of a smooth projective variety. Now, this was also propaganda of why to discuss Hodge theoretical stuff. So of course you guys know very well, but I put here Hodge conjecture because people ask in the sort of colloquium type talks, why do you want to study Hodge theory? So in theory, you can win $1 million. So that's a motivation, right? And if you win, then maybe you collect, right? Unlike the Poincaré conjecture and Perelman, who never collected the $1 million. Right. So I have some pictures. So this is part of my description of the work we did in the Hodge theoretical part of our examples. So I will have lots of Calabi-Yau manifolds of many, many types, and we'll discuss also Hodge theoretical features of them. And so originally, the Hodge conjecture was stated in 41, and there's a comparison between algebraic cycles and analytic cycles. And Hodge stated it in the International Congress of Mathematicians. But the nice thing of Hodge theory is this, that it doesn't matter how many counterexamples exist, the conjectures always continue to be there. So here's my favorite title of any paper in mathematics. I like this one very much. So Grothendieck has this paper, Hodge's general conjecture is false for trivial reasons. It's not a counterexample to the original conjecture, but for a more general version of it. But you will see, I will talk about a different conjecture, which is now for Hodge theoretical invariance of Landau-Ginzburg models, and there will be a similar situation where it was also proved false very soon after state. Okay, now brighter note. So Calabi is 100 this year. So these are Yao and Calabi. So we'll have Calabi-Yao stuff. So my statement is motivation to discuss Calabi-Yao varieties is evidently Calabi-Yao varieties will be good for your health. You see, look at how nice and healthy Calabi is. You can see him in Philadelphia. And he's 100 years old and so in good mood and good health. Okay, so let's go to geometric mirror symmetry. So the original geometric mirror symmetry conjecture is stated for Calabi-Yau varieties, actually originally for Calabi-Yau threefolds. So here I have a Hodge diamond of something which is n complex dimensions. But if you have that, so the statement goes like this. Suppose you have a Calabi-Yau variety that has a diamond of this configuration, then the geometric mirror symmetry conjecture would say that there exists a dual variety or a mirror such that the diamond of the mirror is obtained from this one by exchanging red and black. So that here's the mirror on the 45-degree line. And so if X has this diamond, so its mirror has the diamond obtained by flipping red and black. So here's our diamond. So that's the original one, right? So I have very small illustrations of that. So an extremely symmetric Hodge diamond, therefore elliptic curve can be mirrored to itself. It's a very non-trivial case, actually, mirror symmetry for elliptic curves, but at least in the level of diamond, it looks very simple. K3 surfaces, again, very non-trivial which K surfaces are mirrored to which, but diamonds will be all the same type. The initial example, that was this Candelas, De La Osa, Green, and Parks, where they had a smooth Calabi-Yau trifold, that's here, and this mirror, that was something quite singular, and the diamonds, you can see here the reflection on the 45-degree line. So I won't explain this at all because I will pass to homological one, you see. So until then, this one which was describing the Hodge theory, and a lot more, of course, all kinds of integrals, Gromov-Witten invariants, and so on. But until this homological mirror symmetry conjecture of Kontsevich, the mirror symmetry statements were for Calabi-Yau manifolds. But Kontsevich then generalized that to anything, pretty much, by making in one side symplectic geometry and another side algebraic geometry. The main example is you think that a symplectic variety, the most desirable case is when you have a cotangent bundle of any manifold. And in algebraic geometry, suppose you have a smooth one and you can think of it having a smooth manifold, therefore having a tangent bundle. And so the log of very initial duality here is cotangent bundle goes to tangent bundle. That's the very beginning. But the conjecture is, of course, a lot more sophisticated than that, and I will give a couple of different statements. I have pictures. I always have to actually, most of my slides are pictures. So the first comment is one variety may have many different mirrors, different ones. Second statement is it's not, if you have a variety, you make a mirror, it's unclear completely whether you can get back to the original one. It's not in any way a sort of obviously binary operation. It doesn't necessarily return to itself. And the most exciting part is this, that what if something has no mirror? So Kontsevich himself said that he stated this existence of mirrors because he doesn't believe in vampires, right? So everything should have a mirror. So we'll see. I'll discuss that. Okay, so statement one. So the first This is copied precisely from how it's stated in the proceedings of the ICM, actually. So if you start with an algebraic variety, so here X is the algebraic side. So you start with a projective variety or a subvariety of it. Then there should exist a pair. So the pair is called a Landau-Ginzburg model, where what we want to make is that Y is a symplectic variety and F is a complex function on it, such that the left thing is the Fukaya category, which I will describe, and the right-hand side is the derived category of coherent sheaves on X. That is a lot more known, so I will focus more of my time in the symplectic one. Okay, so here is it described. These are our football illustrations. Bruno did them. So this is Fukaya, this is Kontsevich. And we started making this slide because this homological mirror symmetry talks, all the talks, the speakers were always dividing the board into side A and side B. Side A is always symplectic side, and so one looks for Lagrangian subvarieties, Timbos, morphisms are given by Floor homology. The category is Fukaya category. I will describe some of that, at least by drawings. And on the algebraic side, so you have varieties, sheaves on the varieties, category of coherent sheaves. Homomorphisms are homomorphisms of sheaves and complexes. And in general, one considers scalar manifolds. So we are here, and we want to play the game, right? And assuming the conjecture always holds in every case, we should always have the matches that ended up to be a tie, because everything should have a mirror. Right, so let me describe a bit Landau-Ginzburg models. So Y can be any manifold. We will, in our case, there will be symplectic ones because I will be constructing those Landau-Ginzburg models on symplectic side with a complex function on it. They exist in both sides, and there is also the vocabulary of A side Landau-Ginzburg and B side Landau-Ginzburg that also is there. Right, so here is the drawing of a Landau-Ginzburg model. So family over C. So we have to think of this as Morse theory type of thing. So there is a family, one parameter family. And in this one parameter family, what we look for, first of all, are vanishing cycles. So here's my cycle. As you move along, you get to this singular fiber where it disappears. So that's an informal definition of vanishing cycle, a cycle that vanishes. Something that's in the middle homology of the regular fiber, but not on the one on the singular fiber. So a nicer picture of vanishing cycle. So a same regular fiber may have several. That's actually the more interesting situation that we'll be looking to study. So here I have two vanishing cycles, but even more than that, the objects we want are not exactly the vanishing cycles, but the timbos, which will be like this kind of figures that are here, the yellow ones, which are the figure that you obtain by parallel transport of the vanishing cycle by the gradient flow until it reaches the singularity. So those are the timbos, those are the objects of the Fukaya category. Oh, sorry. Right, so the one case where the Fukaya category is actually well defined mathematically is in what's called Lefschetz fibrations. So Lefschetz fibrations are very well known in algebraic geometry, and the important condition is that every critical point should be of quadratic type. That is Morse type singularity, so non-degenerate singularity, exactly like you do in Morse theory. So that's the main condition. Outside the singular fibers, it should be a locally trivial fibration. So this is written here as a topological fibration only, even though it's a smooth map. And the condition for it to be symplectic, the most important part is that for every regular value, the corresponding, we call it level here, because we had the word fiber appear in too many different situations. So we call this regular level and singular level. So the regular levels should be symplectic submanifolds. There are some non-degeneracy condition around the singularities, but anyway, the continuation, the important part then will be, do they exist, right? So do we start first? So on the algebraic side, we can put any projective variety or quasi-projective variety and write category of covariant sheaves. So there are enormous amount of examples and 450 years extra of history compared to symplectic geometry. Now, in symplectic geometry, on 4 real dimensions, then symplectic Lefschetz fibrations became very popular because Donaldson showed that for a 4 manifold to have a symplectic structure, that's essentially the same as to having the structure of a symplectic Lefschetz fibration. So first, there is the existence of a Lefschetz pencil, like in algebraic geometry, that is a family parameterized by P1. And then, after blowing up finitely many points, maybe we obtain a Lefschetz fibration. So let's suppose that this fibration that's drawn here on the right-hand side is something obtained from this pencil that has this base locus with these red dots. So you can blow up the base locus, you can obtain a topological fibration. This works out nicely. So in theory, for higher dimensions, you could also take Lefschetz pencils in any variety and blow up the base locus and look at the corresponding fibration. However, if you want to do symplectic geometry and you blow up points on this vibration here, on this pencil, then on the red lines, which will be the exceptional loci here and here, the symplectic form will be degenerate. And it will be degenerate in the entire directions here, so that won't be a symplectic form anymore. So it gives you a lot of trouble to fix it if you come from there. There are works of Poseido and some other people where you fix the degeneracy problem by patching a new symplectic form around this using partitions of unity. But then it becomes quite difficult to obtain, to actually follow vanishing cycles and so on. It is hard to handle. So what we wanted to do is to, first of all, to start working on this was to come up with examples of symplectic Lefschetz fibration in whatever dimension. So here comes Lie theory to make up new examples. So there's a change of category, let's say, but it will be extremely useful. So our objects, our symplectic manifolds that we're going to consider will be adjoint orbits of any semisimple Lie algebra. So here's just a definition of adjoint orbit. So the orbit of an element H naught by the adjoint action of the group. Therefore, if you're thinking of a Lie algebra of matrices, that means you choose your matrix H naught and consider all the conjugates of it, and that will give you the adjoint orbit. So it's quite well known that the Lie algebra itself, it comes with a Hermitian form, and if you consider the imaginary part of the Hermitian form, then it will give a symplectic form. Now, we will take the adjoint orbits with this symplectic form. That is very non-standard. The standard form on the adjoint orbits are the KKS, so constant Kirillov-Suryo. However, you see, we then have here's a result that we will use then. So we're together with Linogram and with Martin, both in Campinas, that so we take the adjoint orbit of some element, H naught. Any of them, we're taking that in the Cartan subalgebra. We choose a second element that will give us the height function. That will give me the potential, the function defined on the variety here, or the manifold. And the function is Cartan-Killing pairing with H. So for every element of the orbit, I do this, Cartan-Killian pairing with H. This means, in case of matrices, this means simply take the product of H and X and the trace. So that's the function. So then we showed that using this choice of symplectic form we made, this potential function gives the adjoint orbit the structure of a symplectic Lefschetz vibration. So we're in business. Now we have examples of Lefschetz vibrations in whatever dimension you'd like, as big as you want. You can just choose any Lie algebra, any adjoint orbit, semi-simple, right? Lie algebra, any semi-simple adjoint orbit, right? Choose any element, regular one now, so that the function has isolated singularities. And we have then examples of symplectic Lefschetz vibrations that we can study. The question now is, are they interesting, right? So the first thing is, if one thinks from algebraic geometry point of view, so all these adjoint orbits are affine varieties. You can write them by equations inside the Lie algebra. So it looks very simple. From symplectic point of view, it doesn't look very simple at all. So let's take a look. I always comment on this. So there are finitely many critical points of the function. What are they? So we start with an element H naught, and it has so you choose the corresponding Weyl group corresponding to this theoretical situation, and the Weyl images of the original element. These are the critical points. Exactly those. So we have finitely many critical points. And now, right, how does it look like topologically first? So instead of acting with the group G, I can act with a compact part of it. That will give me a flag manifold. So then it will give me a compact manifold. And so what happens is that joint orbit has the same isomorphism, real isomorphism type, as the cotangent bundle of the flag. Not symplectic, but as a real manifold, it looks like a cotangent bundle of the flag manifold. The flag itself, with our choice of symplectic structure, will be a Lagrangian submanifold, so it exists. So that means that as a symplectic manifold, these adjoint orbits, they contain a compact flag manifold, therefore it's quite non-trivial, even though it's an affine variety, so that flag is not visible algebraically, it's visible symplectically. And more importantly, do we have possibilities of many vanishing cycles? So how does our regular fiber look like? Regular level, as we wrote here. So in general, you take this the Weyl group that will have some finite number of elements, and the homology of the regular fiber, so the middle Betti number, that's important one, the one that's giving us the longest horizontal in the Hodge diamond, that is then, that will consist of k-1 total numbers, right? Because there are k-1 singularities. Therefore, there will be a lot of possibility of vanishing cycles. So, okay, so in principle, we're looking forward to finding many. Okay, before I go to try to look for Fukaya category or anything like that, let me comment on the Hodge theoretical part of that. So, so we want, first of all, let me see here what happens to some of the Hodge theory of these examples we construct. So let's look only at the Lie algebra SLN plus 1. And we denote it by here, LGN. This is the Landau-Ginzburg model we got, which is topologically equivalent to cotangent bundle of projective space CPN. Then there is something called the Kontsevich conjecture. I'll tell quickly very soon what it is. And we showed that such orbits satisfy that. So this together with Eduardo Balico and Francisco Rubilar, who's in Chile, and Louis Saint-Martin. However, the conjecture is false. This is similar to the original one, right? It is Lunds and Przyjałkowski showed the conjecture is false before we show the conjecture is true for those cases. But like I said, that's Hodge theory. Doesn't matter how many counterexamples, you still continue to work on it. It's not like other areas of mathematics. When you have a counterexample, you change the study or change the work. Here you just continue and find more delicate hypotheses. So let me say what kind of Hodge theory this is. So we have some variety and potential in it. This Kontsevich, Kazarkov, Pantev, first step of working with everything is this extremely long list of conditions that are required for you to first of all compactify the variety. So the first thing to do is to compactify, and it's really long. So I want to discuss, I'm just showing it as big and complicated. Now, once it has been compactified, they define three numbers. So I will just show kind of briefly what the numbers are. So the first one is called FQ, and it is some HP omega Q. It's very similar to the things that one does to define the usual Hodge numbers, except this enters with some logarithmic part coming from the compactifying divisor. But there is a sense in which this looks like a definition of the usual Hodge numbers, except it takes into account the function and the divisor where it is actually taking the value infinity. There's a second definition, so it's an HPQ now, second numbers, where you do HP plus Q of this entire space, homology of the entire space relative to the regular fiber, with a lot of grading and details, as usual, right? Also in the usual Hodge numbers, there are delicate grading issues. But again, so this is a different way of generalizing the standard Hodge numbers. Okay, so that's H, and there's a third one called I. These are longer to say. For us, we're actually easier to calculate. So here you have to take sheaf of vanishing cycles. So CY, so this is actually a constructible sheaf of vanishing cycles for a regular fiber. So lambda is a regular value. And then you take the hypercohomology of the complex of constructible sheaves of vanishing cycles. So long to say, but anyway, this is defined directly from the vanishing cycles, and again generalize the standard definition. Of course, there are many conditions which I'm not saying here, but it's long if we discuss in detail. But the conjecture is then the three things agree. That's the conjecture. And then, okay, so it's false on dimension 2 by results of Lunds and Przyjałkowski. And we showed that these three agree on those adjoint orbits of matrices which are of the type like n, and then -1, -1, -1. So all the eigenvalues are -1s except for one of them. So we show the conjecture for that. So okay, so far it's working nicely in that they're satisfying the Hodge theoretical prediction, so that's good. Now let's calculate Fukaya category. Right, so let's try to look, does the mirror symmetry statement work out nicely? In fact, when we constructed examples using Lie theory, then people said, oh, it's all going to be very easy. Lie theory is too standard. Everything is going to be trivial. Okay, fine. So let's calculate, right? So if it's going to be trivial, we should be able to do it quickly. So let's do it. So we're looking for a Fukaya category. Let me illustrate. Here is a case where I have a vanishing cycle that is vanishing to this one singularity and also to the other one. This can happen. It happens. It's possible. It happens as you see in this figure. And this is precisely what's going to happen on the very first example that I'm going to show. So it's important to then keep in mind that the objects are the tymbals. So here I have two objects, one object, two objects, even though there is only one vanishing cycle, but there are two tymbals. So the one on the left, the one on the right. I always show also a physics illustration of a vanishing cycle that I took from Arefeva, from a cosmology talk, this one. So now here my vanishing cycle is this. So you have a collapsing star, it vanishes, it rotates around this axis. So one can see very nicely the consequent, the consequential monodromy that it provokes. So the vanishing cycles come with also corresponding monodromies around the circular fibers. Here's the actual definition of Fukaya category, which I'll then explain by picture. So the category of vanishing cycles will be such that the objects are tymbals, and the morphisms, I'm just writing it down here, but they come from Lagrangian floor homology, which I will explain by picture, because otherwise it's long, and the picture is anyway convincing and useful for us. So you see what the floor homologies will be. Here's a Dan twist picture. So it's one thing to comment, because in each of our examples, we always have that every singularity is of Morse type. That means that the monodromes are always Dan twist. So here is the illustration of a Dan twist. Now, the illustration I'll do of floor homology is using Dan twist. So we copied the equations of the Hamiltonian flow for cotangent of S2, actually, directly from the PhD thesis of Paul Seidel. So it's an old work of Paul Seidel during his PhD. So it goes like this. So now, this blue square is going to represent one cotangent fiber for the cotangent bundle of S2. So what do I want to do? So if we want to do floor homology F0, F1, then the recipe says you deform F0 until it intersects F1 transversely, and then you count the intersections, right? So here's the fiber drawn with equations. Now it is the Hamiltonian deformation. Think of like time epsilon, Hamiltonian deformation of F0, which will then intersect with F1. What is the second guide that I want to use? I want the Dan twist of F1. So again, with equations, this is the picture of the resulting Dan twist of F. It's not just art, it's really illustrated using the equations. So that's the Dan twist, so the second object I'll consider. And now the Dan twist after epsilon deformation with the Hamiltonian flow. And now we need two things, floor homology F1, F0, and then it turns out to be disjoint. So that means that's you deform F1 and then intersect with that F0, and then they don't intersect. And the other way around, so F0, F1, they intersect at a circle. Now, when you look at this intersection, if you move the circle a little bit, it will have two self-intersections. If you think of it like as standing up, there is a minimum and a maximum. So you have 2 points, and these 2 points have different grading. One is 1, the other is -1. Okay, so this we'll need. Now we go to the actual example, and it will be related to the illustration I just did. So let's do the simplest possible example, that is SL2. So I take the orbit of this 1 and -1 element, and I take the H to be this as well. So then the orbit, the adjoint orbit of this guy, consists of all the matrices with plus and -1 eigenvalues. It has a real dimension 4. The Weyl group is just plus or -1, and so the critical points are just the H0 and -H0. Okay, so we have these two guys, and here is the resulting Fukaya-Seidel category of this guy. So it is like this. I have two objects, L0 and L1, like the F0 and F1 that I illustrated. In one direction, they don't intersect, so we get 0. In the other direction, they intersect in 2 points, but of different grading. So you get some Z and some Z -1. And the self-morphisms are that's sort of by definition. So that's our Fukaya category. It's painted in blue. So it looks really quite simple. Okay, so result. So first result is this model that I just showed with this the simple adjoint orbit and so on has no projective mirror. So people said maybe if you compactify, still no projective mirror. What does it mean? It means that if you take any variety, algebraic variety X whatsoever, projective and quasi-projective, and you calculate the derived category of coherent sheaves, it is never going to be equivalent of this blue one. This was great. When we're in Trento now, I came to Trento, this was a couple of years ago or maybe more, but anyway, we were looking for a mirror for this guy for a while. So when I got here and I asked Balico, I want an algebraic variety whose category of coherent sheaves is this. And he had a laugh. It's like, nah, impossible, absurd. So I said, great, we have a theorem now. So anyway, so there isn't such thing. That means that this particular category doesn't appear in algebraic geometry in this way. So in such sense, we have the following state of affairs at this point. So we have a symplectic player. So I called this Cristiano Ronaldo a while ago, this blue player here, with nothing corresponding on the algebraic side, which is, I don't know, great, terrible. It all depends how you want to look at it. But so this is a vampire so far as this mirror is concerned. All right, so now what? What to do, right? Okay, so there is another possibility. I said, if you think of the orbit that we just considered and that has no mirror at all in that sense, right? That's such a strange thing because that orbit is actually a deformation of cotangent of P1. You can write down the deformations very explicitly. At the end, I'll show you that. So Bruno Suzuki just did like very delicate study of these deformations and what's happening and so on. But in any case, it's so strange because if you take cotangent P1, that's toric variety. For toric varieties, here's the game. So Patrick Clark, in his PhD thesis, he showed that if you want to do toric mirror, so you have a variety and a potential. This has two corresponding matrices, div, which is the matrix where you write down the divisors of the variety Y. And there is mon, which is the matrix where you write down the monomials of the function f. And toric mirror simply means exchanging the two matrices. So there is always a mirror in the toric case. In fact, we can cook up the example of projective space to make a self-dual, like on the nose, a very sort of obviously self-mirror, at least candidate to mirror. So that's strange. But right, so if you cook up this potential, then the two matrices are equal and the thing looks mirror to itself. Okay, so let's think of pairs then, not just a projective variety, but a projective variety with a potential on that too. So now it's Landau-Ginzburg model to Landau-Ginzburg model. That's what Patrick Clark really showed, like in his PhD thesis. Consider Landau-Ginzburg models in both sides. So it's as if here you're doing Morse theory in the symplectic point of view, and here Morse theory algebraic point of view. And then this algebraic variety with this potential G has another category that's called the Orlov category of singularities. So that gives you a second statement of homological mirror symmetry, a different one, which to say, if I look at this Fukaya category of YF, I want it now to be equivalent to the Orlov category of singularities of XG. Now, what category is that? So you take the DB the original one, and mod out by perfect complexes. That means things which consist of a sequence like that of finitely many locally free sheaves. So essentially finitely many vector bundles. So a sheaf will be called perfect, or a complex is called perfect if it's of this type, or quasi-isomorphic to that, such so that if your variety is smooth, then this thing will be zero, because then all the coherent sheaves satisfy this type of things. Therefore, this quotient actually measures the singularity of the variety. Okay, then, of Huno, so I have YF, and now I want to look for a mirror. So I want X to satisfy, so that this category will be mirrored to mine, but what's X? So there is a recipe. The difficulty with the recipe, which is Gross and Siebert intrinsic mirror statements, is that they have like 200 papers. Each of them has more than 200 pages. So it's just an extremely long literature. And it kind of goes like that. So you take your Landau-Ginzburg model, you put it inside a log Calabi-Yau pair. Then you have to compute all the intersection complex for it. That's kind of classical. And generalized theta functions, not so classical, but there's a lot extra to the literature. And is supposed to compute not just Gromov-Witten invariance, but punctured Gromov-Witten invariance, which is a longer thing. But assume that you can follow the recipe and you have the ingredients, you can find an equation. So here's the equation that I find if after computing, well, actually asking Mark Rose to tell me how to compute instead of reading also many papers, but that the Gross and Siebert intrinsic mirror symmetry program would then produce this equation. So for this variety with potential just y, then I calculate this category of singularities, and it turns out to be equivalent. So this does give a mirror in this sense. Now computing this category of singularities is long, and also it's very interesting because it's like when you're looking for an irrational number, you know there are very many, but in reality there are three, right? There's only pi and e and root of 2. So that's the same with this. When you want to compute category of singularities, what you want to find are sheaves or complexes that are not perfect. And then I would take the most horrible possible sheaf I could think of, and then the thing would turn out to have a finite resolution, etc., etc. But eventually it worked. So here it is. So that at this point, you see, now I put Orlov here. And you see, it was anyway my mistake to have put Kontsevich here. Kontsevich should be the referee, in which case all the matches should come up tie, right? So 1-1. So now we're happier, let's say, or something like that. Anyway, right, and just now a few comments, but I was also very happy that I got to present this actually in this in geometry and topology section of ICM. It was a short talk, but still, I was very happy to present those and with the football slides and so on. So that was fun. Okay, now I can also do the same. I mean, I can also find the mirror candidates for the minimum adjoint orbits, but only candidates because we have not computed, at least not yet, computed any of the Fukaya categories. Only the case of 2 has been completely done. But I know what is the candidate, and I also know on the algebraic side, I know the full category. I mean, I know the morphisms. So if one wants to do the symplectic part, one at least has a guess of what it should be, because on the algebraic side, I know the full category with the morphisms and everything. Okay, so there's that. And now just extra comments. So we have this Lie potential. I'm calling it Lie potential, the one I showed, using the Lie theoretical construction. But there is also a different thing. So on cotangent of projective space, there is something which is much older and quite well known in representation theory, which is a Hamiltonian action of the one torus, that I wrote here, something very simple. So t minus 1x1 at t minus nxn, and then on the fibers ty1, tyn. That has then the corresponding Hamiltonian vector field, and therefore it has a corresponding potential, because I know that's a Hamiltonian vector field of this potential, but we have this potential. And they didn't look the same to us at all, and we were trying to compare to what happens to cotangent. But then it happens that Bruno showed that you can actually choose things appropriately so that these two things are essentially the same. Not exactly the same, right? Because this is cotangent projective space. This is the orbit. That's an affine space. But in rigorous algebraic geometric language, it then gives a new definition. There's like a million things to be studied now for this definition of what it is to have birationally equivalent Landau-Ginzburg models. And in the sense we say, so the two spaces are birationally equivalent varieties, and the potentials agree on Zariski open sets, so that that comparison can then be restated as the Lie potential and the toric potential on those two spaces are birationally give rise to birationally equivalent Landau-Ginzburg models. So there's now a ton of things to be studied, but we can now look forward to borrowing techniques from representation theory, because a lot is known on representation theory of this part. Okay, now only things to come. So there's a little bit of explanation about the formations of Landau-Ginzburg models now in this language. So this is a depiction of Hirzebruch F2 deforming to F0. These are Bruno's slides of his talk, actually. I just completely copied it. And then the corresponding deformation of Landau-Ginzburg models. And one can write down details to show that you can start with a self-dual one and arrive at the one that had no mirror, and so on, and many comparisons to be done. But I'm about to stop. I'll just mention again the idea of what seems to be happening on the example I mentioned. So the case of the adjoint orbit of SL2, that the original guy that we have, symplectic one, is the one with two critical points in different fibers. And geometrically, it works precisely like the height function on the sphere, with critical points south and north, with the two timbers being like the southern hemisphere and the northern hemisphere. Of course, it's a four-dimensional picture. I'm drawing only the sphere, but the Landau-Ginzburg model that has all this trouble and initially had no mirror, that is just a complexification of the height function on the sphere. Whereas the Orlov category of the space I calculated later looks precisely like you take the same space, not exactly, but very close to it, that the same space but with a perpendicular function, so that both singularities are on the same fiber. And that makes all a huge difference. But anyway, that's what it looked like. There is no saying if something similar should be happening in other examples. That would be great, right? If the mirror is just obtained by taking the function on a perpendicular direction somehow, that would be wonderful, but it seems too good to be true, but could be true. And just a couple more things that I mentioned that we're working together also here with Bruno, is that suppose we think of SL3 now, right? Because I only showed SL2 orbit. Now, see, SL3 has two sort of very clearly different semi-simple orbits. So if you take the matrix, say 1, 0, minus 1, so a matrix with three different eigenvalues as your starting point for your orbit, then your potential will have six singularities. So it's written here as the black points. If you take the matrix to be like 2 minus 1 minus 1, two of the eigenvalues repeat, then there will be only three critical points. But because our potential looks linear in the Lie algebra, you can see how these things move. like how these points flow to the other points. So the black points pair up. You actually add the matrices, you get the other critical points. So there should be a way to show how some of the orbits are deforming to the simpler orbits. So in this case, you can think of maybe contracting the P1 fiber. And so there should be a way to work this out in families when they degenerate. Now I just showed the drawing of what happens to the LCL4 orbit, just because it's pretty, but it's actually calculated with the precise locations, whatever way Bruno did it. Anyway, so a lot to continue, but for today, I'll stop. So thank
Okay.
you so much for listening. And
Okay. Thanks, everybody.
I'll try to do this. Let me see if I see you. Oh, yeah.
Eunice, can you can stop?